So we're going to practice some of the rules for assigning oxidation numbers on here. Basically, the order that you want to go in for assigning oxidation numbers is you want to start with your alkali metals, then your alkali earths, then you want to look for any oxygen or hydrogen, then everything else. And just based on this precedence, we can use the periodic table to figure everything out. Alkali metals are going to have a +1, alkali earths are going to have a +2, oxygens are typically a -2 with very few exception, hydrogens are a +1, and you want everything else to kind of add up to equal 0. So let's take a look at carbon dioxide over here, the first one. We're going to do these in blue. Carbon dioxide, according to the order of precedence, oxygen needs to get its number first, and oxygens all have a -2. Now, even though oxygen has a -2, it has 2 oxygens, and so its total that it brings to the table is -4. Basically, if you draw a carbon dioxide, and I'll draw one up here, you have a carbon double bonded to 2 oxygens here. Each of these oxygens has a -2, and we need the entire formula to add up to equal 0. So that carbon is going to become a +4 right there. On H2O2, this one's special, it's hydrogen peroxide, and it acts strange. I'm not going to test you on this, but the reason that hydrogen peroxide acts strange is because oxygen actually will come with a -1 instead of a -2, and hydrogen will be a +1. If that confused you, don't worry about it too much. It's not on my test. Really, we're more worried about the other ones on here. Let's look at H2SO4. H2SO4 is sulfuric acid. Now, according to the order of precedence, we're going to assign our hydrogen and our oxygen first. So +1 - 2. Now, we can go ahead and calculate the totals here by going 2 times +1 is +2. And 2 times -4, or excuse me, -2 times 4 is -8. Now, if we've got a +2 and a -8, sulfur has to be a number that will get us to 0 using those other 2 total numbers, which means that we'll have a +6. Now, again, that might be a little confusing, but the totals are what we worry about in terms of getting that last number figured out. But the numbers up top have to remain the same for only the individual atoms. So on lithium hydride here, lithium is an alkali metal, so it gets assigned a +1 first, and hydrogen has to be flexible here and take a -1 so that it will add up to equal 0. On sodium chloride right here, NaCl, sodium is an alkali metal, +1. Chlorine is a halogen, so it's a -1. Halogens are -1s almost all the time, so I can add that over here. Right here, add your halogens. And that's going to equal 0, no problem. This one right here, K2CrO4. Potassium, K, is a +1 because it's an alkali metal. And so that gives us a total charge for potassium of +2. Chromium, we don't know. Chromium's a transition metal, and so we're going to leave that one for last. But we know oxygen's a -2, which gives us a total charge of -8. And that looks really similar to the sulfuric acid over here. And sure enough, chromium will have a +6 in the middle as well. For lithium hydroxide, oxygen, hydrogen will come after we assign the lithium the +1 that it gets because it's an alkali metal. So the alkali metal gets it first, oxygen becomes -2, and hydrogen is a +1. That adds up to equal 0. For aluminum oxide, aluminum is special, it always gets a +3, but even if you didn't know that, oxygen having a -2 would give you a total of -6, and aluminum would have to be +6 to get you to 0, and +6 divided by 2 is +3. Last one here, calcium sulfate. Calcium and oxygen will go first. Calcium gets +2 for being an alkali earth metal. Oxygen -2, giving it a total of -8, giving sulfur a +6. Even if you're having a hard time with these, it's going to be okay. The more practice you do, the easier it becomes, and you can come talk to me as well and try and get some help on this. The last thing I want to do for you guys here is show you how to balance an equation. The first thing that you're going to do on these is you're going to go through and assign everybody oxidation numbers. Coefficients in the formula like 3 and 2 do not count towards oxidation numbers at all, so you can almost ignore them. Anything that's alone automatically gets a 0, and alone means it's only bonded to itself or to nothing at all. So iron here will get a 0. It's not got anything to it. So then we've got 3 compounds we have to go through. Let's do this iron oxide first. Oxygen will get assigned first, a -2, giving it a total of -6. And iron needs to make up +6 to get us to 0. So +6 divided by 2 is going to give us a +3 for its oxidation number. Carbon monoxide acts kind of weird. We got a -2 on the oxygen, and carbon becomes a +2 right there. And then carbon dioxide, we have a -2 on the oxygen. -2 times 2 becomes -4, and so carbon has to be a +4. So with all of this, we can now take a look and say, okay, what's oxidized and what's reduced? So oxidized, OX, reduced, RED. And the way that you can tell is that anytime an oxidation number going from the left to the right, so across the formula from one side of the arrow to the other, if the number increases, it's oxidized, and if it decreases, it's reduced. So iron here goes from a +3 to a 0, which means that it's reduced. Okay? Oxygen goes from a -2 and a -2 to a -2, so we can just ignore oxygen completely. Oxygen is neither oxidized nor reduced, so we leave it alone. But carbon here goes from a +2 to a +4. That number is an increase, and so we say that it is oxidized. That's why we don't put these big numbers on the top. We leave them down here, because otherwise they'll get us confused and we won't be able to tell what is oxidized and what is reduced.